Good afternoon, dear students. Today we will discuss about the topic solving recurrence relations. As we have already came in different kind of recurrence relations in your merge sort, quick sort, and also your heap sort algorithms. Okay, and in general, the recurrence relations as of the form, as you know, Tn is equal to A into T n by B plus Fn. This type of recurrence relations you have made. But in general, the recurrence relation will be Tn is equal to alpha T n minus beta, it can be there, plus alpha 1 Tn minus beta plus alpha 2 T beta plus f of n. It may be like this also. Hence, we will solve some kind of the solution of the recurrence relations of any form or the possible form which can be done by using three methods. One is your substitution method, another is your recursion tree method, third one is your master theorem or master method. Now, you see substitution method, what happens in your substitution method, what will happen? You will guess the solution. You will guess the solution because you will substitute the solution and verify the solution using the method of induction and solve for the constant. For what constants that recurrence relation satisfy, either for the, that means for your big O notation, the constant is your say C1 and N0. For theta notations, there are two constants C1, C2 and N0. Like this, all these constants you will solve in case of solve the constant. Hence, in the substitution method, you have to guess the solution and then you have to verify the solution by using method of induction or prove the solution by using method of induction. Then you will solve the constant. And generally, using the solving recurrence relation using the substitution method is difficult because you need the some kind of expert knowledge on that. Now let us take an example where this recurrence relation is used to solve using substitutions. Let us consider a recurrence relation Tn is equal to 4 into Tn by 2 plus 100n. That means this is your Fn. Now this is value is your Fn. Now what happened? You will assuming that at the beginning that T of 1 is theta of 1, which is say equal to a constant unit of time. Now you will guess. First of all is guess. Guess. Suppose you guess it is big O of NQ. That means big O of NQ. You can prove it separately for omega of NQ and also theta of NQ. Now you assume that this is the solution. Now you will solve, prove it by or verify it by method of induction. Since you will assume that Tk for any value of k, say k is less than n, this is true or this is true. That means it is big O of n means it is less than C of n q because you are assuming that the solution is a power of 3. Hence it will be less than this. Now prove that Tn is less than equal to Cnq. You have to prove this because you have to verify this by using the method of induction. Now what happens? Once you will, if you will do it, then what will happen? Then Tn is equal to, as it is 4, Tn by 2 plus 100n. Now in this case of n by 2, what will happen? You will put C into n by 2 whole cube. And this 4 is coming in this case because you are assuming that for any k less than n, the assumption is satisfying. Hence for this you have to replace it because you have assumed. Hence this you will simplify it and you will get this. And this then what is it? C nq, then C nq by 2. That means C nq by 2. Hence that means Cn by 2 into nq. Hence you are adding again Cn by 2 into it becomes Cn cube, and subtracting the same unit, and again this is 100 NQ, and that means just you have simplified from this to this mathematics. Now you see this is Cnq, which is less than, because this is a term n is always positive, and this term you are subtracting from this, hence this term is less than equal to Cnq. That means Tn is less than equal to Cnq. That means you have verified that. Hence for that, third point is that you have to solve the value of C. Hence this will be greater than equal to 0 if C will be 200 and n will be greater than equal to 1. If this condition is satisfying, then this will be positive, and hence C and Q will be greater than this T. Hence you have solved the constant. Hence this way you can solve the recurrence relation using substitution method. Hence in this case you have to also handle the initial conditions, that is ground the induction with the base cases. These things you have to do. Now in this case what will happen, the bound is not tight, because the algorithm, the recurrence relation we have followed here, and we have proved that it is of the recurrence relation we have followed here, and we have assumed that this is NQ, but really it is not NQ. This is not provide exact upper bound, or it is a somewhat bound is somewhat more. That means it is not provide you too tight. Hence what will happen, another can assume that it is of big of n square. For this you have to prove this by using this. Hence what will happen, hence in the recurrence relation Tn is equal to 4Tn by 2 plus 100n. Hence in this case what will happen, it will be replaced by C n square, because you will put a Tn by 2, which is what is n by 2 to with a n by 2 whole square. Hence it will come this, and this will, hence it will be equal to less than equal to Cn square. Now okay, hence what will happen in this case, what will happen, you will find certain hence this is what will happen, no choice for C is equal to greater than 0 choose. Okay, for hence what will happen, in this will not happen. Now if you will prove the tight bound, for this what happens is, similarly if you can say the lower bound of this, and you can prove that C2 is equal to greater than 100 in a similar way. Hence my point is that this is the way that the substitution method works, but generally this way of doing the solution of recurrence relation using substitution method is not it's very difficult to do it, and it is basically done those who are well known about analyzing the algorithms, or the highly experienced persons. Now another is the recurrence tree method, and we have already solved the recurrence relations of some recurrence relation using recursion tree method, that is your merge sort and your quick sort. In this case recursion method, what is happen, the recursion model, the cost of a recursive execution of an algorithm. Now here what will happen, this recursion tree method can also provide a good guess for substitution method also. Okay, that means let us see how it is happening. Now suppose this is a recurrence relation, and that is Tn is equal to Tn by 4 plus Tn by 2 into n square. Now how using recursion tree we will solve this. Now you see this Tn can be replaced by what is, initially it was Ctn, initially it was this is Tn. Now this can be replaced by Tn by 4, Tn by 2, this is 2 node, and n square is the cost of to reach this one and this one. Hence this Tn will be written as this point is n square, and here what will happen, 2 node will be created, one node is for Tn by 4 and another node is for Tn by 2, like this. Hence you will see this thing will come. Now again what happens, this will be breakdown, this will be breakdown accordingly, that means Tn by 4 it's n by 4 means that means it will be Tn by 8, and here it will be Tn by 4 means Tn by 16, and here it will be t n by 8, n by 8, and here it will be, in this case it will be n by 4 square, like this. Hence what will happen, you will check it, this will be the situation. Like that it will go on doing the doing this. At last when we are reaching to the n value 1, and in this case what is this, is the recursion tree. If we will follow this recurrence relation to construct a recursion tree as we have already constructed. Now the cost of this recursion is nothing but addition of the cost in each level, addition of the cost in each level. And in this case the height of the tree will be in this case, you see the addition of this level is n square, the addition in this level is this, similarly the addition in this level is also what is this is equal to 25. You can do the addition of this, you will get 25 by 256 n square. Like this, if you will go on adding, what happens, the final total addition will be what happens, this, if you go on adding, it will go n square into what is happening, first one is 1, then second one is 5 by 16, and plus then next one is 5 by 16 whole square, and like it. That means this, if you are considering this x, that means x whole cube, if this we are considering this as x, plus x whole 4, like this it will go on. That means here x is less than equal to 1, because 5 by 16, 5 by less than equal to 1. Hence for this is a geometric series. And this, for this geometric series, you see this is, if x is less than if x is less than 1, then we can write this as 1 by 1 minus x. Hence what will happen, 1 by 1 minus what will happen, 5 by 16. Hence it will be what happen, that means 16 by 11, like this. Okay, that means it will be a constant. Hence what happens, this will be a these terms, whole the term will be a constant. Hence this will be equal to c of n square, hence it is equal to theta of n square, because we have exactly calculated. Hence it will both provide the upper bound and the lower bound. Hence if you will follow this recurrence relation to solve using recursion tree, we can find that the time complexity, or sorry, the complexity of this, or the growth of this algorithm is bounded by theta of n square. Okay, now we have already solved other recurrence relations in your as in your mod chart. We have solved the recurrence relation Tn is equal to what is happening, 2t n by 2 plus Cn, and that at that time we have told that Tn is equal to what is theta of n log n, and we have also proved the same case using the recursion tree. Hence the recursion tree you can use to solve the this kind of recurrence relations. Okay, now third one is your master method. See, in master method, as I have told, suppose if the recurrence relation is like this, Tn is equal to a Tn by b plus Fn, where a is greater than equal to 1 and b is greater than 1. A is greater than equal to 1 means why these two things will be greater than equal to 1, this will be greater than 1. See, if a will not be greater than equal to 1, that means it will be less than 1. That means the original problem we are subdividing subproblem, negative subproblem, which is not considered, because if a problem is, this is not considered, and b is greater than 1, that means the original value of number of inputs will be always less than the input. The input cannot be increased in this case. If this is the situation, then this will for this type of recurrence relation, the master method can be applied. Now let us see how this recurrence relation master method is happening. You see, if you will follow the recursion tree for this, it will be a Fn. That means this will be Fn by b, because how many times? This is a times. This is a times of this. This is one time, second time, third time. This is a time, because you see this is a time n by b. Hence what will happen? If Fn, this will be what is Fn by b. Next page Fn by b, like this. How many times? A times. Again this will be, again if you will subdivide it, if fn square b, n by b square, like this will go on. And here how many times? In one node will be a times. If there are n nodes, that means here it will be a square times with this value, a square time with that means a square of f of n, f of n by b square, like this. And in this next case it will be a cube, a square into a cube times into f of n by b cube, like this it will go on. Okay, like this, as I have already told, it will go on. Now what will be the height of this tree? See, height of this tree will be h of log n base b. If it will be, instead of height is n, h is a log n base b, because the problem is divided into this one, n is divided into n by b. You see, if fn tn is equal to n is equal to 2 t n by 2. In this case, what happens? This is log n base 2 here. Hence, but here it is the number of height will be h is equal to log n b, because what happens? Like this, because here in the binary case it will be b is equal to 2. Hence, what this will be the height, hence label will be just one more than. Now, the point is that how many leaves will be there? Leaves will be just a to the power h, a to the power h, because leaves will be number of leaves will be a to the h, and because height is h, then number of leaves at the last level will be a to the power h, and instead of h we can write log n base b. Hence, this, as in mathematics we have already shown a mathematical identity that this will be n to the power log a base b. Okay, this will be the leaves. Now, in order to apply master theorem, we will compare the fn value . Now, in order to apply the master theorem, we have to compare fn value with the leaves values. That means which one is dominating, whether fn is growing, order of growth of fn is bigger than the order of growth of leaves nodes, or the it is less than the order of growth of fn is less than this, or they are have equal order with multiplication of something. Depending on these three cases, your master theorem has three clauses. Hence, what happened? You see, first case, if fn is equal to big of n log b by a, what does it indicate? See, what does it indicate? See, first of all, see what is indicated. Fn is equal to big of n to the power. That means it is corresponding to your leaves, the cost of the leaves nodes, hence minus epsilon. That means the leaf nodes, the growth of leaf nodes is greater than the growth of the root node. That means the leaf nodes dominate. The leaf node dominates the growth of the, that means the root node. Hence, the total time complexity will be bounded or will be taken by or the time complexity will be as per the what is leaf nodes, or that means the cost at the leaf nodes. Hence, Tn will be theta of n log a base b. Hence, you see, as I have already told, that means in this case, what happens? The total cost, actually the total cost will be cost of this, cost of this, cost of this, up to cost of the leaf nodes. But this is less than the leaf nodes. Definitely all, that means all these nodes is less than the leaf node value. Leaf node value. Hence, everything you can, what is, that means this one will be dominate. Hence, the weight of the increase geometrically from the root to the leaf nodes. The leaf node hold a constant fraction of the total weight. That means leaf node if holds the constant fraction of the total weight. Hence, that means the time the Tn will be what is, it will be theta of your the leaf node value. That is your n log n to the power log a base b. That means it is n to the power log a base b. Because these internal these nodes are less as compared to these nodes, growth is less as compared to the leaf nodes. Even if taken together, they are holds a constant fraction of the total weight of the leaves node. That means leaves node hold a constant fraction of the total weight. Hence, case 1 will be that means in this case, if this is satisfying, then your Tn will be theta of n to the power log a base b. In the second case, what is happening? If that means second case we will compare Fn with n log b. That means again we are comparing Fn with b. The first case, every time we are comparing first case, this growth of Fn is less than the growth of this. Hence, the time the complexity is dominated by this. And the second case, if in this case situation, that means neither Fn nor this are that means they have what is your that is your leaf node and your Fn are equal. That means in this case, what is everything you have to add. That means Fn value is same as your leaf node values. That means their growth is same. That means for some constant k is equal to 0. If we will put k is equal to 0 here, because k is greater than or equal to 0, that means Fn is equal to theta of n log a base b. That means Fn and your leaf nodes n to the power log a base b are of the same order of growth, are same. That means Fn and n log n are go at the similarity, and in that case we will say that Tn will be these the leaf nodes with this factor, because this factor arise, because if this factor, how this factor arises? See, the growth is like this. Neither your leaf nodes nor your root are dominating, though they are going equal with this constant. See, in this case what happens? If you will draw a tree, that means everything we will add. Everything we will add this, we will add this, we will add this up to this. And what is the height of this? Height of this is your log n base b. Height of this log n b. But this is, that means this growth is equal to your what is log k log to the power k n into your n to the power log a base b. The growth of this value is same as this. This addition of all these things is same as this. Adding of all these things is same as this. Adding of the last labels also this. That means how many times we are adding these times? That means your height. That means height time. That means log n base b times n. That means again these things will be multiplied with log n with base b. That means it will be, the final will be, that is the Tn will be what is happening? The total complexity will be Tn will be how many times? This into log a k to the power n plus 1. Hence it will be log what is k plus 1 n base b and into this what is theta of, that means as I have all the theta of this into your, that means the time complexity will be Tn will be that means equal to theta of your n log Tn will be your is equal to theta of n log a base b into log nb to the power k plus 1. Because previously if you remove the why this plus 1 is coming, because this is the this thing, if you leaving this plus 1, the cost of all these are log n to the log a b log n base b to the power k, but this plus 1 is adding because every times this thing is adding 1 part, hence how many times it will add log n b, hence this plus 1 is coming. That means in each level we are evaluating this, and there are how many levels? That means log n to the power base level. That means that's why this plus 1 is coming, because in each level this one is coming and I have this much of level, hence the time complexity will come like this. Okay. Hence now the third case. In third case what is happening? That means if your Fn is omega of n to the power log a base b plus epsilon. In this case, which one is going faster? You see, in this case, this one is the lower bound, provides a lower bound. Let us say omega means lower bound. That means Fn is going faster than this. If Fn is going faster than the leaves, then that means the Tn will be dominated by your Fn. Tn will be dominated by your Fn. Hence, Tn will be theta of f of n. Theta of f of n. And in that case, the regularity condition you have to take that A f of n by b is less than or equal to C of f n. If this regularity condition satisfied, then only we can write Tn is equal to theta of f of n. Okay. Now, this is the same case as in the last two cases we have given an induction. The weight decreased geometrically from the root. That means f of n is bigger than the root. That means the weight decreased geometrically. That means the weight of this is less than the weight of all its root. Is less than the weight of all these roots like that. That means this one is greater than this one is greater than this like this. That means the total one is contains the root holds the constant fraction of the total weight. Hence, in this case, what will happen? This time complexity will be dominated by your f(n), by the root values. Okay. Hence, this is the case. Now, let us take some example. Tn is equal to 2Tn by 2 plus n. That is, it is the what is your recurrence relation of your Morse-Hotel. No, it is not Morse-Hotel, because in Morse-Hotel this one will be 2. And this is some kind of recurrence relation. Here A will be A is 4 and your B is 2 and your what is n to the power log A by B. That means this case this is n square. This is the value of your leaf nodes and this is the value of your what is root node. That means your leaf node is going faster than your root value or the node value. That means here f of n is equal to big O of n square minus epsilon. Here we are choosing epsilon is equal to 1. But you can choose other epsilons also. Here epsilon is equal to 1 because it is f of n is equal to n. Here it is, that means epsilon is equal to 1. Hence Tn is equal to theta of n square. Which rule it is? Case 1 it is following. Now similarly another case, in this case what happens? Your Tn is equal to 4 to n by 2 into n square. Here instead of n it is n square. Now we will check what is the value of A. A is this 4, B is this 2 and now n of A log B is equal to this is n square. Now f of n is n square. That means they have equal case. That means f of n square with the same as your leaves, but here k is equal to 0 here. K is equal to 0 here because f of n is same as your theta of n square. Theta of n square because this and this growth are same. Hence here k is equal to 0. That means hence k is equal to 0. Now your what will happen? You can say that Tn is equal to theta of n square log k plus 1. That means here k is equal to 0. Hence it is equal to log n square log n. Now let us consider in this situation. In this case the same thing, but here it becomes nq. It becomes nq. Now A is equal to 4 as usual, B is equal to 2 and this is equal to n square and f of n is equal to nq. Hence which one is dominating? Now your f of 1 is dominating that, and that means n square growth is less than the nq growth. Hence it is f of n is dominating and n square. This one is giving the lower bound with some epsilon. Here you can check epsilon is equal to 1. That means in this case what happens? You will check the regularity conditions and for C is equal to half, the regularity condition is satisfying and hence Tn is equal to theta of nq because it follow the case 3. Case 3 means it will be by the Fn and Fn is your nq. Okay, because Tn is equal to, you are right, what is it? Theta of f of n and here f of n is your nq. Hence you are putting this is the solution of this relation. Okay. Now, but in this situation, in the master method, this situation, in this example, in the last example, the master theorem cannot apply because this will not come to any such type of either first rule, second rule or third rule. Hence, the master theorem does not apply. Hence, that means using the master theorem, you may not possible to apply all kind of recurrence relations. But most kind of recurrence relations you will see in your algorithm design classes will follow this master theorem or master method. Okay, hence I am stopping the class here.